Yo, yo, yo. Welcome to 4.2. So, 4.2 is solving systems again, but this time we're going to have three variables. So it is going to make it three-dimensional. So that's pretty crazy. And it's basically what we just did, but on steroids. So we're going to talk about the steps for solving systems. In your guided notes, you have you have drawings of possible solutions. So we'll talk about those real quick. We'll just go through those. And we'll do the example so that you can see what that means. So the possibility is that you could have a consistent and independent system which has one unique solution. But three-dimensionally, we're talking about a plane that may be going this way, another one that may be going this way, and another one, say, that may be going this way. But they will all intersect at only one unique point. Again, you have the 3D image there in your notes so that you can see what kind of a solution that looks like. So I've labeled my different equations different colors so that we can work through these. So first thing you want to do is make sure that they're in this format where you have x, y, z, and then equal to the constant. A, b, and c are just the coefficients of x, y, and z. Okay, so what I want to do is I want to choose two equations and eliminate the same variable. So I'm going to go through my variables and look at like my x's. They're not opposites, none of them. I'm going to look at my y's, none of them are opposites. I'm going to look at my z's. Okay, well these two are opposites. So the smartest equations to choose to eliminate z by adding them together are 1 and 2, because when I add them together, the additive inverse is right here with this z and negative z will sum to 0. So I'm going to take equation 1 and equation 2. Now make sure you don't make a lot of copy errors and don't skip too many steps here, or it's really easy to make mistakes. Okay, so I'm going to add equation 1 and equation 2 together, and I'm going to call the new equation that I get here equation 4. So this is the equation 4 that I'm going to refer to. So again, I chose two equations, which were equation 1 and 4, and I'm eliminating z by making them additive inverses. Well, they already are, so now I'm going to add these equations together. I'm going to get 4x plus y, that's going to sum to 0, and I'm going to get equals a negative 14. This is my new equation 4. The next step is I'm going to choose two other equations. So obviously I'm either going to have to choose 1 and 3 or 2 and 3. Those are the only other options. And I'm going to eliminate the same variable. So I'm going to say, well, if I just eliminated z, which two equations are going to be easiest to eliminate this z here? So this is a negative 2z. I'm going to want to choose equation 1 because it's already an additive. It's got a positive and a negative sign, but I will have to multiply equation 1 by 2. So I'm going to do that. So this is my equation 1 multiplied by 2, and here it is. Equation 1 multiplied by 2. Remember, it goes to every one of these, so we're going to distribute. So we will get, for my new equation 1 multiplied by 2, a 6x minus a 2y plus a 2z is equal to negative 30. Okay, and I'm going to scoot this over just a bit. So this is multiplied by 2. Let's see, we get 6x again minus a 2y plus a 2z is equal to a negative 30. Now I'm going to write equation 3 here. 2x plus 3y minus a 2z is equal to 0. Again, I chose the same variables to eliminate. I chose z. If I'm going to eliminate z, every time I choose my equations, I have to eliminate z. Now I'm going to add these together and get my new equation 5 is what I'm going to call this equation. So when I add these together, I'm going to get an 8x plus y. These sum to 0, that's why I did that, is going to be equal to a negative 30. So again, both times here, these sum to 0 and these sum to 0. That's the point, is I'm eliminating z. So now I have I chose two other equations and eliminated the same variable as I did in step 2. Okay, now I'm going to use equations 4 and 5. So this is where what we did yesterday, or last time in 4.1. I'm going to eliminate a variable. So right here, I've got a positive y. Right here, I've got a positive y. So I just have to multiply one of these equations by -1 to make these opposites. Here, I'd have to multiply this equation by a -2 to make it the opposite of 8. So if I wanted to choose to eliminate x's, then I would have to multiply by a -2 here, or a -1. So I'm just going to multiply equation 4 by a -1. And again, I have to multiply every term. And I'm going to write this here, equation 4 multiplied by a -1. And that new equation then is going to be -4x minus y is equal to a positive 14. Now I'm going to add those together. So I'm using equations 4 and 5 to eliminate this variable here, to eliminate y. Okay, so when I add these together, they're going to sum to 0, and I will just get that 4x is equal to -16. Well, now I have my x value. X is equal to -4. We're not there yet. Okay, so I still was doing step 4. Now I've eliminated two variables. I've eliminated my z's through steps 2 and 3 and my y's through step 4. Excuse me. Now I'm going to back substitute this value. Well, what does that mean? Well, if x is -4, then I can substitute that value into either equation. I'm going to substitute that value right here into equation 4. So I'm going to back substitute into either equation 4 or 5. I'm going to plug this -4 for x in right here. Okay, so we've got 4 times -4 plus y is equal to a -14. So I'm going to get a -16 plus y is equal to a -14. When I add the 16 to both sides, then y is 2. So now I have my y value. Now I need to back substitute both of these values here. If x is -4 and y is 2, I can back substitute that into an original equation. I'm going to choose equation 2 just because. So in equation 2, I'm going to substitute the value of -4 right here for this x. -4 plus a 2y, which y we know is the value of 2, minus z. I should have done it into equation 1. Minus z is equal to 1. Okay, so I've got -4 plus 4. Well, those cancel each other out when I add them together. So I'm going to divide by a -1 and get that z is a -1. Okay, so I now have my x, my y, and my z. I'm going to write the answer, step 6. So this was the back substitute values, so I substituted x into equation 4 or 5, and then I'm going to substitute the value I get for y. Then I'll have x and y, and I can substitute those back into equations 1, 2, or 3. Step 6, I got to write this as an ordered triplet, so it's -4, 2, and -1. So real quick, we have 3 solutions here because we have 3 variables. And notice that every time we add a variable, we add a dimension. So when we had x equals 3, that was just a dot. But when we have y plus x equals 3, that is a line. It was 2-dimensional. But when we have x and y and z, then we now go into a 3-dimensional plane. Okay, so this is an example of a consistent and independent system with one unique solution. Okay, and again, you'll have to look at your graphic there on your guided notes to see what that looks like or could possibly look like. Okay, the next type we're going to do here is an inconsistent or no solution type of problem. want to, again, note that you need to be looking at those guided notes to see what an inconsistent no solution system would look like. Basically, there's no point that lies on all of them, so they could maybe be like stacked, like 1, 2, 3, but they're parallel, but in different planes, so they're never going to cross. Or maybe they're stacked and one crosses like this, but there's no point that lies on all three. Okay, so that's what that looks like. Okay, so example here of that, we'll do equation 1 is going to be 2x plus a 4y minus 2z is equal to 3. Equation 2, we'll do negative x plus y minus z is equal to 6. And equation 3, we'll do x plus a2y minus z is equal to 1. So the important thing here is to work smart. So I want to eliminate a variable. So I'm going to look at my x's and say, oh, okay, it wouldn't be hard to use 2 and 3 to eliminate x. That's good. There are no, my y's I'd have to multiply, and my z's I'd also have to multiply. So I'm going to start and I'm going to eliminate x's. I'm choosing x because it's the quickest one. So I am going to, out the gate, add 3, 2 and 3 together. Okay, so I'm not adding equation 1 here, I'm just adding equation 2. In this step, I'm just looking at equation 2 and 3, and I'm eliminating x. When I add these, the x's sum to 0, and I get a 3y minus a 2z is going to be equal to 7. Okay, that's my equation 4. So I want to rewrite and do as little work as possible. So that's my equation 4. So we just eliminated x using 2 and 3. Now I want to use a different equation to eliminate x again. I'm going to use equation 1. So I'm going to get 2x plus a 4y minus 2z is equal to 3. And I'm going to use equation 2, but equation 2 is going to be multiplied by 2. So that new equation 2, let's see what that is. So I'm going to take and multiply equation 2 by a2. And I'm doing that because I need these x's to be additive inverses. This one's 2, I need this one to be negative 2. I'm not looking at any other part of the equation. I don't really care how it affects the rest of the equation. I'm only trying to eliminate x. So I'm going to get a negative 2 x plus a 2y minus a 2z, and that's going to be equal to 12. Okay, so now I'm going to add these together, and this is going to give me my new equation 5. Sorry. Okay, those x's are going to sum to 0. That was the point, right? These right here sum to 0. And I'm going to get a 6y minus a 4z is equal to 15. All right, now I'm down to 2 equations and 2 variables. I'm going to use elimination one more time. So this is step 4. I'm going to use equations 4 and 5 to eliminate another variable. I'm going to multiply, I'm going to eliminate y. This one has a 6y, so I need this one to be a negative 6y. So I'm going to multiply this equation right here by a negative 2 to make them additive inverses. I'm going to write my new equation 4 multiplied by 2. Okay, but this has been multiplied by 2. And that is going to give me right here a negative 6y plus 4z is equal to a negative 14. Okay, and when I sum these together, this sums to 0 and this sums to 0, and I get this 0 is equal to 1. And you're like, whoa, wait a second, where'd the variables go? Well, it's the same thing from the previous section, but if the variables go away, okay, and you have a false statement here, this is really important, if this statement is false. What this means, previously it meant parallel lines, but because we're talking about three-dimensional and 3 different planes now, this just means that these lines never intersect at one place. They could intersect, or two of the lines could intersect, or maybe none of them intersect. Again, you'll have to look at the guided notes to see what an inconsistent no solution system looks like. All right, the next possibility here is a dependent solution with infinite systems. Sorry, a dependent system with infinite solutions. Again, you'll look at your guided notes to see possibilities of visually what that would look like. But if they're all three the same equation, then they would be 1, 2, 3, all of them, and they would share every point that is in that plane, whatever the plane looks like. Okay, so there'd be an infinite number of solutions. They could also intersect by making kind of what looks like a fan, and the line that they intersect on could have an infinite solutions, because this plane would go on forever. Okay, so what does that look like? Well, my equation 1 here is going to be x minus a 3y plus a 4z is equal to 2. My equation 2 is going to be negative 2x plus 6y minus 8z is going to be equal to negative 4. My equation 3 is going to be 1/2 x minus 3/2 y plus a 2z is equal to 1. So in this one, it's going to require a little more upfront work because I need them to be in this format, and this one right here is not in that format. So if you have to, you need to clear the fractions. We've talked a lot about how to clear fractions, but we're going to find the LCD. In this case, the LCD is 2. So I'm going to build up each of these fractions to have a denominator of 2. And when they do, if I multiply the entire equation by 2, then the bottoms would go away. Okay, so my equation 3, after I've cleared the fractions, let's rewrite it, is going to be x, because there's just one x, minus a 3y, plus a 4z, and that's going to be equal to 2. So I want you to notice something, that after we clear these fractions and you start looking, you're like, well, that one has x, that one has a negative 3y, that one has a 4, that one has a 2. You're like, oh my gosh, these are the same. If these equations are the same, that does not mean that this will have infinite solutions, because we need to see if this equation is the same as well. So can we do something to this equation right here to make it be the exact same? To make it x minus 3y plus 4z equals 2. Well, if I take equation 2 and I divide it by a negative 2, okay, I'm going to divide it by a negative 2. So I'm going to divide this negative 2, x by negative 2, that's going to give me just an x. If I divide the 6 by a negative 2, that's going to give me a negative 3y. If I divide the negative 8 by negative 2, that's going to give me a positive 4z. And if I divide this negative 4 by negative 2, that's going to give me 2. And you can see here now that equation 1, 2, and 3 are the same equation. They were just in different forms. So if these are all the same equation, that means that this looks like the one where it's like a paper on top of a paper on top of a paper. They're all in the same plane. So that means that this does have infinite solutions, because every point in that plane would be a solution to this one, to this one, and to this one. So we're going to get this is infinite solutions. But how do we write infinite solutions, or how do we know which ones are solutions? Because just because I have, let me grab 3 papers here. Just because I have, these 3 papers, and let's pretend like they're all the same, right? But these are the 3 different equations, and they're lying like this, 3-dimensionally. This point right here is not on that plane. This point right here is not on that plane. This point down here is not on that plane. So none of these points that aren't on the plane are solutions, but this entire plane is a solution. So how would I say that? How do I say, well, the whole dang plane is a solution and it goes on forever, so it's going to have infinite solutions. Well, the way that we're going to say that is we're going to say, oh, well, I'm going to say that x, y, and z are such that, I'm just going to list this first equation here, x minus 3y plus 4z is equal to 2. So any point that lies in this plane right here, because it's the same as this one and the same as this one, makes this statement true. Okay, so any point that lies in this plane makes the statement true. So right here's the solution. Here's how you would write that solution, but understand that means there's an infinite number of points that you could substitute to make this statement true. Okay, I just want to go through one more example and then this section will be done. So let's do equation 1 is 2x plus 5y minus 3z, and that's equal to 30. Equation 2 just has an x and a y, there's no z, what the heck, is equal to negative 3. And equation 3 has a 2x minus a z, and that's going to be equal to 0. So this one doesn't have a y, this one doesn't have a z, and that kind of makes it maybe a little confusing. Well, they're all in this ax plus by plus cz format. You can just think of this as having a plus 0z and a plus 0y. Okay. So now when I'm trying to eliminate, I should work smarter here. So this equation is already eliminated for z. So if I wanted to eliminate z from another equation or to form another equation, I would use equations 1 and 3 and eliminate z if I chose z. Now, this equation has already eliminated y. So if I wanted to eliminate y, then I would choose equations 1 and 2 and eliminate y. Okay, so I'm going to go for z just because we can. So that means because I'm choosing z, I need to understand that my equation 2 is actually my equation 4 because it already has y eliminated. So this means when you're given a problem that looks like this, you're actually ahead of the game. They've done step 1 for you. Now I'm going to use equations 1 and 3 to eliminate z because z's already gone. So equation 1 is going to be the 2x plus 5y minus 3z is equal to 30. I need equation 3 for this z to be the additive inverse. That means that I'm going to take this equation, the whole thing, and I'm going to multiply it by a negative 3 because I need this to be a positive 3. So when I distribute here, okay, then I'm going to get now for my new equation 5, for my new equation 3 times negative 3. So negative 3 times equation 3, that is going to give me a negative 6x. Well, 0 is just going to give me 0, there's no y. And then I'm going to get a positive 3z, which is what we were looking for. And that's going to be 0 times negative 3 is 0. Now I'm going to add these together. And my equation 5, okay, my equation 5 is going to give me a negative 4x. Going to bring down that 5y. These sum to 0. That was the point. And that's going to be equal to 30. Okay, again, so I made it so that I could eliminate these z's. They sum to 0. Now I'm going to use my equation 4 and 5 the same way that we have all along and make one of them additive inverses. Well, I'm just going to eliminate x because it's quickest. This is a negative 4, so I need this to be 4. So I'm going to multiply equation 4 by 4 to make this x a 4x because I need it to sum to 0. Okay, so my new equation 4 down here that's been multiplied by 4. Okay, so 4 times equation 4 is going to give me a 4x plus a 4y is equal to a negative 12. All right, well, these sum to 0, and I'm going to get 9y is equal to 18. Divide by 9, and y is 2. Hallelujah, I've got one value. Now that I know what y is, I'm going to take this value of y and back substitute it into equation 4. Okay, so I'm going to have x plus 2, because that's the value of y, minus 3. Subtract the 2, and I get that x is negative 5. Okay, now I've got my x value, and I want to find my z value. So we can plug that back into any original. The problem is if I try to plug it into this original, there is no z, and if I try to plug it into here, there's no y, but maybe that's not a problem. Let's try plugging this into here, the x value, into equation 3. So in equation 3, I get 2 times x, which is negative 5, minus z is equal to 0. Okay, well that's a negative 10 minus z is equal to 0. If we add z to the other side, then negative 10 is equal to z. Oh, okay, well I got the value there. All right, so that is the ordered triplet. So I'm going to write this as an ordered triplet. The x value is negative 5, the y value is 2, and the z value is 10. You're always going to write it as an x, y, z. So this is my solution, and this means that these all intersect at one specific spot. The last thing that I want to do is I want to check this answer. Okay, so I'm going to erase all this work, but keep this solution here. So I'll write the solution right up here. I've got negative 5 to negative 10. I'm going to go through one example of how to check and make sure that when you get this, that it is correct. So remember that what this says is this is the one point that all of these share. So when I plug these points in, they should make each of these statements true. So let's see if statement 1 is true. 2 times negative 5 plus 5 times 2 minus 3 times a negative 10 is equal to 30. Okay, well, this is a negative 10 plus 10 plus 30 equals 30. Those sum to 0, and 30 does equal 30, so this is true. So this point lies in the plane of equation 1. It's a plane because it's three-dimensional. Does it lie in the plane of equation 2? My value for x is negative 5. My value for y is 2. And that's going to be equal to a negative 3. Well, that does indeed equal a negative 3, so that's true. So we know that this point lies in this plane. Great. So that checks off 2 of them. But for it to be the solution, it has to lie on all 3 planes. So when I plug this value in here, I've got 2 times a negative 5 minus z, which is a negative 10, and that's going to be equal to 0. Well, this is a negative 10, and this is a plus 10, so 0 does equal 0. That is also true. Now, again, you should always check, but I'm not going to take the time in the videos to check every single solution that I get. And of course, if you have an inconsistent solution that says no solution, there's really no way to check that, and same with infinite solutions. But if you get an actual ordered triplet, you can plug it back in and check to say, hey, is it true in all of them? If it is, then it is a solution to this system.